Thanks, Coleman. My name is Masako Yamada, and I'm the Director of Applications Development here at IonQ. Going back to this full stack chart, I'd like to direct your attention to the topmost bin, which is highlighted in orange. And that is where our team operates. Our applications team works very closely with enterprises in the private, public, and government sectors. And we work very closely with our partners to develop hybrid quantum algorithms that address both their technical and business needs. We are a team of PhD researchers, scientists, and engineers who span all STEM disciplines. And our three main focus areas are chemistry modeling, optimization, and AI and machine learning. On the next slide, I'd like to talk about some of our partners and some of the works that we've done with them. The first three examples we've actually talked about already in previous webinars, so I would just love for you to look at them and take a note that we have talked about these examples before. Today, I'd like to talk about the latter two examples with Oak Ridge National Lab and ANSYS. And in particular, I'd like to talk about a new hybrid optimization algorithm that we've been developing that is applicable to these and all optimization algorithms. On the next slide, I'd like to talk about on the next two slides, I'd like to talk about a novel algorithm that we've been developing with our partners, including with Oak Ridge National Lab. The algorithm is called QITE, Quantum Imaginary Time Evolution, and this is an optimization algorithm that really works well with contemporary quantum computers. First of all, I'd like to step back a little bit and talk about optimization and how these problems or the set of optimization problems can be applied toward many industries, including cargo loading, flight gate assignment, energy grid optimization. And in this case, we are also talking about optimizations for computer-aided engineering. And one of the things that I'd like you to envision is optimization as a landscape. Often we talk about optimization in the context of a landscape that has hills and valleys. And really the problem that we're trying to solve is if you have a landscape of hills and valleys, mountains, divots, how do I get to the bottommost point of that landscape? It's a little bit counterintuitive, but in the field of optimization, the bottommost part of that graph or that landscape is where we want to be. So maybe if you can analogize, you can think of the landscape as being cost or energy or distance. And the solution is how can I reduce or minimize the cost or the energy or the distance of whatever it is that I'm trying to solve. So if you can imagine, if I had a marble on this landscape and I wanted to go to the lowest point, sometimes the marble could get stuck in a divot, not even know that it's at the bottom and think that it's reached a minimum. That would be an example of what's called a local minima, not the global one. And that is an example of a case where the optimization did not quite work out. Another example could be if I'm a marble in a landscape and I hit a very wide flat plane and the marble doesn't go any further. Again, that's called a barren plateau. And it's an example where the system isn't allowing the minimum solution to be found. So one of the challenges that we have as any optimization algorithmist, especially in quantum, is how can we mitigate some of these challenges that are faced when we try to develop optimization algorithms. And we believe that this QITE algorithm is a step in the right direction toward avoiding these pitfalls. Next, please, on the next slide, we'll talk about one very specific plot from the paper that we recently published with Oak Ridge National Lab. You're welcome to read the paper by scanning the QR code on the right there. But really what I wanted to talk about is really dig into this one chart to explain a little bit more what this optimization is about. So first of all, I'd like to circle back to a slide that Margaret showed earlier around our quantum computers. And our quantum computers comprise ions in a row. She showed that slide of ions in a row with two laser beams zooming on two ions. So in our quantum computers, we have something called operations or gate operations. and that really involves the laser shining at 1 or 2 ions. So you can either have a single qubit gate operation where the laser shines at 1 ion, or 2 qubit gate operation where the laser is split and shines on 2 ions, and then those 2 ions interact with each other. So one of the real hallmarks, or one of the advantages around quantum computing, is considered to be when those qubits are entangled with each other. So they are interacting with each other. That really leverages the inherent quantumness of the system and enables us to basically capitalize on the strengths of quantum physics to help solve our problems. Another thing that's really important to consider is that as these lasers are addressing these qubits, you really want to try to minimize the number of operations. Why? There's really two reasons. The first is that the shorter the number of gates, the faster the time to solution. But also, the shorter the circuit, the more accurate the solution. So really, we are motivated by the desire to get to the bottom of that landscape as quickly as possible and in the right well. So on the right-hand side, what we show in the dotted lines are actual examples where our algorithm was able to quickly get to the bottom of that landscape with fewer iterations than other methods. And this is, as I mentioned, one of the really exciting steps in the right direction toward coming up with a quantum optimization algorithm that can achieve these dual purposes of getting to the right minimum in the minimum amount of time. The other thing that I wanted to point out here on the right-hand side is we ran these on actual IonQ hardware, which is becoming increasingly important. I was looking at the chat here, and one of the observers basically said that with the increase in the number of qubits, it becomes harder and harder to simulate a quantum computer using classical methods. We are rapidly reaching the point where classical computing can no longer simulate the number of qubits that we have. So when we get to that point, the option that we have before us is to be able to run this on hardware. And by showing this at this number of qubits, we are very confident that as our roadmap expands and we have more qubits, we will also be able to run these simulations on those QPUs as well. Next slide, please. Finally, recapping our pillar areas of chemistry, optimization, and AI/ML, I wanted to show a sort of buffet of the kind of hybrid algorithms that we've been able to develop in partnership with our customers. In particular, I've been here for about 2 years, a little bit more than 2 years, and I've seen some version of this slide, or actually contributed to some version of this slide over the entire 2 years, and I'm really happy to say that this list is growing dramatically. And what I wanted to invite the audience members today is if any of these use cases resonate, or if you don't see your particular use case here, but would like to be part of this growth, please feel free to reach out to us, and we can see if we can do something together in this rapidly growing field. So next, I'd like to hand it off to Bjorn Flott, who's the head of emerging technologies, and he will talk about really the foundational layer of this full stack, which is our hardware. So thanks, Bjorn.
Thank you, Masako. My name is Bjorn Flott, and I lead the emerging technologies team here at IonQ. I'd like to take the next couple of minutes on